I'm going to leave this open a little bit so I can hear you at the end. Okay, so I think we got the recording going. So for today, I'm going to talk about off resonance excitation and excitation. So I mentioned this a couple times before, and I probably went over it a little bit too fast. So so hopefully this time I'll go over slow enough so that it might be more understandable. So this is it, kind of going back to the block equation and going back to thinking about the rotating coordinate system. So the basic idea here is that we're this is basically something that happens all the time. So the first thing to consider is that if you say you put on a gradient and you feed in a small band of frequencies to select a slice, what's going to happen is, because the gradient is on, there's going to be different resonant frequencies in different parts of the brain. And so if you feed in a narrow band of frequencies to select one slice, other parts of the brain that are resonating at different frequencies are going to receive off-resonance excitation. So this is something that it's relevant for magnetization transfer. So mag transfer, because that's something where you stimulate at say you've got water at this frequency, so this is frequency, and then you have a more broad band of resonant frequencies. And if you stimulate with a frequency band that's away from the water, and then wait for the magnetization to transfer between these guys that got stimulated and the water, and then measure a signal in the water, that's called magnetization transfer. That involves off-resonance excitation. But the other big thing where we mentioned off-resonance excitation was in arterial spin labeling. So arterial spin labeling. And the idea there was that we put this gradient on and we let the spins go through the gradient. So I'll talk about that again. So those are several examples of where off-resonance excitation is relevant. But what we want to do today is just sort of talk about how to think about it. And so the problem is that you've got, if you go back to the block equation, you've got precession happening. So there's precession happening, and then there's like T1 regrowth, T2 decay, and then on top of that all, while that's happening, you have the excitation, and the excitation is yet another resonating signal, another rapidly changing signal. And so all those things are going on at the same time, and you have to sort of try to visualize this, and the stimulation signal might not be exactly at the same frequency as the Larmor, resonating protons, the precessing protons. And so trying to visualize like two different frequencies at the same time, that's really what the topic of today is basically just a way of thinking about it. And so we'll start off with the main idea. Main idea. So the main idea is to examine the M vector. So basically keep these two separate. So we've got the B vector, and the B vector has, B0 and B1. That's the applied field. And then we have the M vector, which is the sum total local magnetization of the resonating proton. So don't mix those up. So we examine the M vector in the rotating coordinate system. Coordinate system set to wrong frequency. So set to wrong frequency. And what frequency are we setting it to? We're setting it to off resonance B1. So, off resonance B1, that is not the center frequency. So that's the center frequency. That's not the Larmor resonant frequency. So why would you want to do that? So what we're trying to do is sort of visualize what happens when you've got some resonating protons, they're precessing protons, and then you're hitting it with something that's actually not the right frequency. So you're rotating another thing that's not the right frequency. So how do we sort of visualize that complicated situation? So to do that, let's just back up to the basic idea of the rotating coordinate system. So when we talk about the rotating coordinate system, when we first did this, what we said was in real life, you've got a situation where you've got a big B field, B0 field, and then you have a M vector, and the M vector is precessing around, here's the little dm dt. It's precessing around the, put that arrow there. It's precessing around the B field very rapidly. So this is, lab frame. And then when we went to the rotating frame, the idea was we now spin ourselves around at the same rate as the precession frequency. And when we do that, then basically, let's draw that slightly bigger. So here's the B0. There's the M. And then here's the precession. So this is the dm vector dt. Okay, so that's the coordinate system start. So this is what we did before we did off resonance. So before off resonance, we're just going to sort of like review the rotating coordinate system. So in the rotating coordinate system, what happens? Well, what happens is you completely stop the movement of the M field, and so of the M vector. So here's the M vector. You just stop it in its tracks, because now we're spinning around exactly the same speed as the precessing protons, and so now we just see them completely stationary. So, and that's typically the way the whole time when we were talking at the beginning of the semester about doing a flip, that's implicitly the way we're thinking of it. We're thinking of the magnetization vector as just stopped, and then we flip it down to the to the y-axis, say, and then it slowly recovers up. That's the way we sort of conceptually think of it, as opposed to sort of imagining that it's actually sort of whipping around like that and then slowly going back up while whipping around. So what's the big advantage of doing that? So remember the basic equation. The basic equation here for this was the way we figure out how to update this. It's basically just the m vector crossed with the b vector. So that's this thing right here. That's how we got this guy right there. So it turns out in the rotating coordinate system, so if we now look in the so what was the advantage of the rotating coordinate system? Rotating with B1 added. So the advantage is that we could use that same equation to figure out what the B1 is going to do, because that equation applies to B1 as well. See right here, it's just completely general. It just says B, and that B includes both B1 and B0. So what happened here in the rotating coordinate system? It's as if we set, it's as if we set B0 to 0. As if B0 went to 0. So what does that mean? Well, it means that there's no precession anymore, because basically if you set B0 to 0, there's nothing to sort of cause this gyroscopic precession, and so you just have a stopped m vector. So now that it's conveniently stopped, we can think about applying the B1 vector. Now the B1 vector, of course, is also stopped. So this guy, so when we go to rotating, the meaning is it's as if we set B0 to 0 and then also stop B1. So B1 is stopped as well. So now everything's very simple. We just have a stopped B1 and a stopped M, and then we can apply this equation. So that's the critical thing, is that the critical simplification. So here we have, our B0 this way, and we've got precession, but when we think about adding some B1, that's the high frequency RF into things, once we move to the rotating system, it stops the B1 and it stops the M, but it also stops the B1. And then we can just apply this equation again. And so when you apply that equation, what do you get? Well, you get, you'll basically get a dm dt like this, that sort of rotates, around this axis here. If we apply the B1, say, in the x-axis. So if that's the x, y, and z. So if the direction of the B1 is in the x-axis, then that will just, it'll do something just like precession. It's just exactly like precession, except now it's with stopped vectors. So it will cause a slow precession of the stopped m vector around the x-axis, around the b. So here's the b, so in this case we got the b up here and we're going around this way. In this case we got the b this way, and we're going around this x-axis. So we already knew that. So that's the starting point. So now let's consider, so this was just a review. Yes, review. I put that. System review. Okay, so now let's consider the off-resonance situation. So the off-resonance situation is, imagine, so now we're in off-resonance land. So now imagine that we move to what we have over here. So let's do this. So move to, so we'll move M1, the M vector, to rotating coord from the B1 that is at frequency that's lower than the center frequency that the protons, that M1 is resonating at. So now what happens? So now what happens is it looks like some precession is there. So it makes it appear basically as if, so let's put the M vector over here. So now, even though we're in the rotating coordinate system, because we've set the frequency wrong, it causes this guy to precess. So this guy, it starts precessing. So we get a slow, it's not as fast as the Larmor, so slow precession. How do I spell precession? Jeez. Yeah, I can't spell. Slow precession around, z-axis. So what does that mean? That means it's as if there is a B0. So a fake B0 has appeared. So instead of B0 being exactly 0, which would stop the precession, it's like some fake precession has occurred in the rotating coordinate system. And what is that, what is that frequency of precession? It's basically just going to be, equal to the frequency difference. So if here's the center frequency that the protons are actually precessing at, and then here's the frequency of the B1, it's just the difference between those two frequencies, and that will tell us basically the strength. So this basically tells us the strength of apparent B0. So we can cut with the gyromagnetic ratio. We can just calculate what the this B0 is, and so what it's going to be. There's going to be some small B0 in there. So now let's just try to draw that. So the problem is that we've got we still have the B1, and we have the B0. And so how do those all fit together? So let's just draw a situation, sort of an off resonance, off res with stim from B1. So if we draw our coordinate system here, I'll draw this big because there's a bunch of junk in it. So the first thing is, here's our extra B0. So this guy, we'll just call this, so this is, this is our extra BZ. So what is this guy? This is our extra BZ. that equals the frequency offset divided by gyromagnetic ratio. That's just to sort of turn it into a B, and that thing is times the unit vector in the k direction. So that's the k, which is the z direction. K equals, so here's z and y and x. Okay, so that's our sort of fake fake B0. So there's in real life there's a really big B0, but we went to the rotating coordinate system and then we set the frequency off, and so now it appears that we have a small B0, this extra B0. Okay, but now we're actually stimulating also at the same time. So here's the B1 field, and since we're in the the mistaken rotating coordinate system that we picked corresponds to the stimulation frequency of the B1, this guy's going to be stopped. So this guy is stopped. So here's our B1. Here's our B1 vector. It's stopped. Stopped because the rotating coordinate system that we picked was the B1 frequency. And so what's the bottom line? Well, we're going to get an effective B0. So this guy is B effective. That is the vector sum of those. So of the B1 plus this fake B0. So then what happens? Now we have to put the M vector in there. So let's put the M vector, say, here. Okay, so that guy is you can see what the problem is. Okay, so this guy is the M vector. So that's our current magnetization vector, and we're going to try to figure out how that guy gets modified. And so how that guy gets modified is to apply this same equation. So we just apply the same M cross B equation to this guy. So that's M, and so M is going to precess around this B effective. So M will precess around B effective. So we can still, in this messed up set wrong coordinate system, we can still apply that same basic relationship. And so what is that going to do? That's going to cause this M vector to precess around this offset B. So it'll be something like that. So it's going to, so the dm, so the last insult is, here's the actual sort of precession vector, the next update vector that you get from doing the cross product. So this guy is the dm dt. So there it is right there, that guy. So what that tells you is that instead of precessing around the z-axis, it's going to precess around this offset B effective axis. You know, what's happening in real life? Well, you've got the really rapid precession from the B0, and then you've got some other B1 that's going around slower, and that's kind of hard to keep in mind at once. Here now we've sort of stripped it down, and we've got this slow precession, which is like a flip, the way we think of a flip here in the stationary, when B1 was stationary and M was stationary. We just think of it, you apply the B1 in the x-axis, and it just rotates around. It just rotates around the x-axis. So the same thing is happening here, except it's in a tilted. It's tilted off the z-axis. So several things can cause this. So let's add all the different possible things that can cause this. So one of the things that can cause this so if we figure out this B effective, so this B effective, the B effective vector. So one of the things that we included was the basic off-resonance effect. So that was whatever that offset frequency is times the unit vector in the z direction. But we could also apply a gradient. So, and we're certainly applying gradients all the time. So this is, a real life situation. So if you apply a gradient, the gradient is going to change the resonant frequency. And so so that's going to mess things up relative to the rotating coordinate system that we chose, which was the B1 frequency of the coordinate system, of the B1 frequency of the stimulation. And so we have to add in whatever the gradients, so, whatever the gradients did to the z component. And the x gradient will change the z component moving in the x direction. The z gradient will change the z component moving in the z direction. So any gradient will do this. And so that's the amount of the gradient is going to have to, whatever it did to the z component is going to add to this B effective. So a gradient will sort of have the effect of changing this fake BZ. And then finally, the other thing is the actual B1. So here's the amount of the B1. So how much B1 stimulation did you do? And that could be applied at different phases, but here we'll just say that we're going around the x-axis. And so in that case, it's multiplied by the x unit vector. So this was, for example, phase of B1 around x-axis. So that's the whole equation for all the things that can affect this. And so the gradient might come on and have a similar effect to the off resonance by essentially changing the omega 0. Okay, so what is all this? So if you're like me, I looked at this tilted off resonance thing. Didn't make any sense. Didn't make any sense to me at all. So I said, why do I care? So let's look at how you can actually end up getting an inversion. You could actually do inversion recovery. You could do a 180 degree flip using this off resonance method. So before we do that, let's consider. I'll put the whole summary picture here, but let's consider two other situations. So say we got rid of this B completely. So here we have a B that's in the positive z direction, and it's causing this B effective vector to move down toward. It's causing the B1 vector to move up from the x-axis, because normally the B1 vector would be stopped on the x-axis, and then the m vector would be somewhere, and you would cause the m vector to rotate around the stopped B1 vector. So when we add this fake B0, it lifts the B effective vector off of the x-axis. But what if we got rid of it, so we were right on resonance, well then we would just go back down to the B effective being right along the x-axis. But now what if instead of having the off-resonance system set to a too low frequency, we set it to a too high frequency? Now we would have the other possible situation, which is there'd be a fake BZ vector that was negative, and then we would add that on to our stopped B1. So here's our B1. Here's our fake B0. So we would add that onto and so we would get a B effective that was down this way. So now what'll happen if we add an M vector into that? So if we have an M vector into that, so here's an M vector. So there's the M vector. So what's going to happen is that M vector is going to basically be precessing around this B effective. So here it'll be going, say, should be going that way. So it'll be going like something like that. So it'll be going that way. So that's the dm dt. So it's just the opposite of this, so we could have the same thing sort of going on underneath. But now you're beginning to see how you could possibly use this as a method of inverting the spins. And so the way you would do it, you would just basically, sweep the RF. And that's kind of, so, we could sweep RF, low to high, passing through the resonant frequency. That's one way of doing it. But equivalently, we could do what we do with ASL, which is it has the exact same effect, but it's kind of it's the reverse. So we could either sweep the RF, leave the resonant frequency the same, don't mess with the gradients, for instance, leave the resonant frequency the same and just sweep the RF. But alternatively, what we could do is allow spins to move through, move along, not through, move along gradient. So that would be, here's the brain, here's a blood vessel coming up into the brain. Put a gradient on like that direction, and then have the spins, so the spins, meaning blood, will just sort of be moving through this gradient. And so as they go up through the gradient, they'll be changing their frequency. So you can see that that's basically the same as keeping their frequency the same and sweeping the RF. So you can sort of sweep the RF and keep it the same, or you can allow spins to move along the gradient and then keep, B1 same. So here we sweep sweep B1 freak. So here we sweep B1 frequency from low to high, passing through the center frequency. Here we allow spins to move. So right at the middle of the gradient, we would be at our center frequency. So in this case, we allow the spins to move along the gradient, keep the B1 the same, but the end result is exactly the same. you're off resonance, and then you're on resonance, and then you're off resonance on the other side. Same effect here. So what does this, what does this look like if we sort of think of it over time? So if you think of it over time, we start off far off resonance. And so what does that mean? That means we'll be precessing relatively rapidly. Remember, this is fake precession, but we'll be precessing relatively rapidly around the positive z. And then as we start to get closer to on resonance, we're going to, be effective will be something like this, and then we'll be sort of precessing as a result of the B1 stimulation around an offset axis. Then when we hit on resonance, we'll be precessing exactly around here. So so in this case, our effective, I should draw the effective B1. So here's the effective B1, and now the effective B1 is like that. Now the effective B1 is like that. So this is, I'm leaving out the other vectors. This is B effective. That's this guy here. Okay, so now what's going to happen? So I didn't draw the M. There will be an M vector in each one of these that's precessing, but let's just leave it out for now. Okay. So as we continue to higher and higher frequencies, what's going to happen is then our effective B1 is going to be along the negative axis. Here's the negative axis of the z-axis, and so the precession is going to be kind of like that. And then finally, when we get to far above the omega 0, we will be rapidly precessing with the fake negative effective B0. So now we'll be over here. Or effective, B effective, which includes the fake B0 plus the actual B1 oscillating field. So then now we'll be like that. And so at this, you can sort of think of this, so this is, this was the first condition where we have, B1 freak below omega 0, and then here, B1 freak equals the resonant frequency, and then here's B1 freak above. So what this corresponds to is basically just, it's extremely straightforward. You just basically, if this is the center frequency defined by what the current gradient and what the current B0 is, all you do is you just ramp your frequency like that. So this is time going in that direction. So you just ramp through the center frequency. So it's kind of strangely simple. So if you do that, what you'll do is you'll just do a very nice inversion of spins. So this will do, so the effect of that is to do a very sort of gentle, efficient inversion of spins. And this is called an adiabatic pulse. That's referring to the gentle aspect of it, not wasting any energy. Adiabatic pulse. And it's particularly easy. You just basically just ramp. You just ramp the frequency. And so you just make a sink and then slowly change the width of the sink. If you want to make the, just change the, you don't change the width of the sink, you change the offset of the sink. And so that's explains why you can just sweep the frequency and do it. If you have, what is the problem with this? Well, the problem with this, why wouldn't they do this all the time if it's a really good, kinder, gentler way to do a flip? The problem is this takes time. It takes a long time to sort of sweep the frequency instead of just doing a little pulse with a narrow band of frequencies. And so whenever you have the time to do this, and an example might be, okay, with MP Rage. So with MP Rage, we have a pulse sequence where you do an inversion pulse and you wait a while and then you start doing a readout. So you've got time to kill, and so you can do a long adiabatic pulse to get a nice inversion, and then we're going to wait anyway. We're going to be waiting anyway, so it doesn't matter if you take time. You wouldn't normally do this with a spin echo scan because it takes too much time. If you want to do a bunch of 80s, you can't do this. But you would do it with something like an MP Rage, and you would do effectively the same thing by having the spins pass through the gradient and thereby change their center frequency while keeping a constant B1 on. So that's basically the same thing. So that's what you would do for ASL. So this applies to these two completely different pulse sequences. So this is like flow-driven, flow-driven continuous ASL, or pseudo. You could do the same thing with pseudo-continuous. So PCASL. Okay, so that time I think I went through it slow enough that it was understandable, and so I think we'll end the recording here. Stan?